In this lesson, we are discussing surfaces in R3. By R3, we mean three-dimensional space. A sphere is an example of a surface in R3. Picture this amoeba-like shape. It's a lumpy surface. Now remember, a surface is just that. It's like a blanket. Both of these surfaces do not include the points inside. These are hollow objects, if you will. The points inside are not on the surface, but these two surfaces are unique in that they bound some region inside them. This next surface should be familiar to you. It's a simple plane. All the points on the plane are the surface. This plane does not enclose some bounded region. Here's another lumpy surface. This one also does not enclose some bounded region. Take a look at this familiar surface. It's a cylinder. Now, this does not have a top, so if I came in, I would enter without any obstruction, and then I would exit out the bottom, again, without any obstruction. There are, in fact, points inside this surface that are not on the surface, but it is not bounded because we have this open top and this open bottom. These are all surfaces in R3. We are now going to discuss quadratic surfaces in R3. Before we do that, let's look at some quadratic equations in R2. Y equals x squared is a good old-fashioned parabola, and x squared plus y squared equals 9 is a good old-fashioned circle. These are quadratic for their quadratic term, or terms, but you should recognize that one is a function and one is not a function in R2. Here's an example of a quadratic surface in R3, or more generally, the equation that you see here. And this is where the notes packet will pick up. You will notice here that the quadratic terms are positive. Each of the quadratic terms are positive, and then the n, it equals 1. Now, one way to determine what this shape will look like is to take slices into the shape and analyze what we call traces. That's the sort of cross-section of each slice to determine what the shape will look like. This chart illustrates what some of these said traces look like. If we take the xy trace, or you might think of that as the plane z equals 0, and we slice into this object, then we have this ellipse. In a similar way, if we let x equals 0, that plane slice into it, we have yet another ellipse, y equals 0, yet another ellipse. So when you slice into this thing at different directions, parallel to the different planes, we have an ellipse for each of the traces. And so you might guess what this object looks like. Any guesses on its name? It's called an ellipsoid. And if we go back to the original example, this would be an ellipsoid. Now this ellipsoid would have the center 0, 0, 0, and it would have different radii. The r radius would be 2, the y radius would be 3, and the z radius would be 4. Now here, this quadratic surface, this ellipsoid, we would say in this case that z is not a function of x and y. So instead of thinking as the vertical line test, here think of these spikes that come from z down, and notice that I cross the surface once and I cross the surface twice. So another spike might come down, cross it once, cross it twice. And since each of these spikes go through more than one point, z is not a function of x and y. We could also, in a similar fashion, say that x is not a function of y and z. Picture the spikes that come in from the x direction. Well, it would touch the surface once, and then on the way out, touch the surface again. So x is not a function of y and z.
Just a quick point of clarification here. You will notice that there does exist a vertical spike that passes through only one point. But that doesn't matter. In order for this to fail to be a function, we simply need the existence of one spike that passes through more than one point. You could have several that pass through only 1 point, but the minute you get just one vertical spike that passes through more than 1 point, this thing will fail to be a function.
Let's take a look at the second general quadratic surface. This quadratic surface has two of the quadratic terms being positive, one of the quadratic terms being negative, and it also equals 1. Now, it doesn't have to be the z that's negative. The x could be negative or the y. And if we analyze the chart with our different plane traces, we will see an idea of what this object looks like. So, in the end, it ends up looking like this. We have an ellipse from the top view, but then we have hyperbolas if we view it from the side views. I'll show you the one hyperbola looking at it straight on, and a hyperbola if you view it from this angle here. This has a nuclear tower sort of feeling to it. Now again, the z-axis here, see, there's no top and no bottom, so it crosses through without obstruction. Now this shape is called a hyperboloid of one sheet. A hyperboloid of one sheet because it would take just one sheet of paper to model this surface. And in this general case here, where the z is the odd one out, the negative, we would say this is a hyperboloid of one sheet that tunnels about the z-axis, about or around the z-axis. In this example of a hyperboloid of one sheet, the x is a positive, the z is a positive, and the y is the odd one out, and we equal 1. So this tells us that we have a hyperboloid of one sheet that tunnels about the y-axis, as we can see in the drawing. In our next quadratic surface, we have now two negatives and one positive equaling 1. And our front view and our side view produces hyperbolas again. When z equals 0, we have no graph, no trace. But I'm going to add another trace here. Let's add the trace, let's say z equals 3. If I plug that into the equation, I'm going to get something along the lines of x squared over a squared plus y squared over b squared equals positive 1. And we know that that shape is going to be an ellipse. So let's take a look at what this drawing looks like. Here we have like two cups going in opposing directions. This is called a hyperbola of two sheets. Two sheets, as it would take two sheets of paper to model the shape. Notice here, as z is the odd one out, it's positive while the other two are negative. That means this one will open in the z direction, as you can see here. Consider this example here. We have positive, negative, positive equals 1. So we know we have a hyperboloid of two sheets, and this one will be opening in the y direction. I will show that drawing right now. You will also notice that hyperboloid of two sheets, like the hyperboloid of one sheet, are not functions. See, there is a vertical spike that would pass through more than 1 point, not a function. Here, a vertical, or let's say a y direction spike, passes through more than 1 point, not a function. So y is not a function of xz, and up here, z is not a function of x and y. Now, let's scroll down here for just a moment, and let's take a look at a final example for this page. Here, z is going to be the square root of 1 plus x squared plus y squared, and we're going to describe this shape. Now, you will notice that if I square both sides here, I'll get z squared equals 1 plus x squared plus y squared, or said differently, z squared minus x squared minus y squared equals 1. Well, there we have our pattern. We have positive, negative, negative. So z is the odd man out, and so this thing will open in the z direction. But if we come back to the beginning here, so z is restricted, z must be positive, so this is going to be half of a hyperboloid of 2 sheets. And this one opens only in the positive z. Sort of weird, we call it half hyperboloid of 2 sheets, so really it's 1 sheet, but the general shape is that of a 2-sheeter, but this is only one of those 2 sheeters, as you can see here. Now, in this case, z is in fact a function of x and y. So if we take verticals from the z, all of them will pass through at most 1 point on the surface. So we do have a function here because it's half. Okay, moving on to the fourth one. You will notice here that we do have another odd man out, plus, plus, minus. The difference here is that it equals 0, not 1. So the odd man out could also be the positive one. Multiplying everything by negative, we will get negative, negative. Positive equals 0. So there's one odd man out. And as we analyze the table, we see that we have what is called a cone. A full cone here. Cone. And the cone opens in the direction of the odd man out. Now, considering this example, we see that y is the odd man out, so this will be a cone opening in the y direction. I think in an earlier problem, I had the y direction coming out at us, and that's okay. We are permitted to draw it any way we like, but in this course, traditionally, we treat the y going horizontally like this. So this cone now is opening in the y direction. In this example here, we will also have a cone, but actually it's only going to be half a cone. So z squared minus x squared minus y squared equals 0. Z has to be positive. We have the structure of a cone, odd man out, but this one is going to be a cone, and this cone is opening only in the positive z. So the next time you order ice cream, you really should be ordering a half cone. So here's my half cone with some delicious ice cream on top. And if you don't order a half cone, what they really should be giving you is this ice cream cone that opens up in 2 different directions, and you have to do a balancing act to make sure you eat all the ice cream without it falling to the floor. The half cone here is in fact a function of x and y. Z is a function of x and y, but in the example above, y is not a function of x and z. And whether you have a full cone or a half cone, it is customary to identify the vertex. And both of these cases, the vertex is 0, 0, 0.